Welcome to the Kentucky Watershed Academy. This is Module 4, Dealing with Data, and in this presentation we're going to be discussing collecting data. What are the requirements for watershed planning? As an overview of this section, we'll be talking through some of the basics of water quality monitoring, the equipment used, the parameters that need to be assessed, site selection, and sampling logistics, as well as some data quality levels. First, we want to briefly cover some of the more common equipment that you'll encounter in water quality monitoring technical reports. For measuring basic physicochemical parameters in the field, there are a range of options depending on the price and required accuracy or sensitivity. Basic field parameters include dissolved oxygen, pH, conductivity, and temperature. Separate kits are available from different manufacturers with the total cost around $200 to $250 depending on the initial set of equipment that you purchase. This is the type of equipment that is provided to citizen samplers in Kentucky's Watershed Watch program. If you want to pay a little more initially to get results faster and more accurately, the same information can be collected with a multi-parameter water quality meter, also called a sonde. These start at around $1,000 and can cost over $5,000 depending on the quality of the instrument and the capacity of the data logger. There are also field instruments called colorimeters that can measure commonly collected laboratory parameters. These provide immediate field results based on the color of the vial after a chemical reaction. A colorimeter can run a spectrum of tests and costs over $1,500, while single parameter colorimetric kits can be obtained for $50 to $100. A turbidimeter, which measures water turbidity, can also be added to some multi-parameter sondes or purchased separately for around $500. Streamflow can be measured in a variety of methods, again with the cost increasing with accuracy. To get a very simple estimate of streamflow, a measuring tape of around 100 feet, a wooden ruler or yardstick, and a stopwatch, and a weighty object such as an orange can be used. While a great method for volunteer, this method is less accurate than other methods. For more precise measurements, a top-set weighting rod can be combined with an electromagnetic, Doppler, or a price-type meter and can be used in conjunction with a tape measure to measure the flow. These meters begin at around $5,000. This will allow for accurate time of visit measurements. For long-term measurements, continuous monitoring stations can be constructed and pressure transducers installed. The stream will have to be surveyed and flows routinely measured in order to develop staged discharge curves that correlate the depth of the water to the stream flow. A power source and telemetry may also need to be installed to transmit results. The cost can exceed $10,000. This is necessary if you need more comprehensive assessment of the flow regime. For collecting samples in the field, you'll need some clean bottles, a pen and paper to record the custody, and a cooler to keep samples on ice. Deionized water is also needed for cleaning equipment. Depending on the depth of water, hip waders or chest waders may also be necessary. If field filtering is required, for instance for orthophosphorus or collection of chlorophyll A, then a field filtration system with a hand vacuum pump will be necessary. This can cost less than $100 depending on the equipment type that's used, but it can also range up to $300. It should be noted that if such equipment is used for orthophosphorus, cleaning procedures are extensive and can utilize hazardous materials. If you want sample collection to occur automatically, or to composite samples, that is, to collect numerous samples over a time span and combine them into one representative samples over the course of a storm, for instance, an automatic sampler can be installed. This can be helpful if sampling is in a remote location, if you're doing stormwater runoff sampling, pre-treatment sampling, or other automated needs. For biological surveys, including habitat, aquatic macroinvertebrates, and fish, a range of equipment is utilized. For habitat, just a camera and a data sheet is required. A tape measure to record the length of the reach and the depth of water or the height of the banks may be helpful. For macroinvertebrates, a 1/4 meter square quadrant is used in conjunction with the kick net to sample riffles. D-frame nets, a sediment sieve, sorting trays, tweezers, buckets, and sampling jars and vials are also necessary. For volunteer sampling, you might want an identification key, but for bioassessments, this identification will occur in a laboratory. For fish surveys, seines are used as well as backpack or boat electroshockers, nets, and buckets. You'll probably want a key for this in the field, and a few jars just in case you need to hold on to a specimen. For watershed planning, some sort of erosion survey will need to be accomplished. This may be as simple as just taking pictures along with the GPS location and measuring the height and length of the stream bank that's eroding. A protractor may be helpful to estimate the bank angle, or a clinometer may be used if more exact measurements are necessary. A gravelometer may be used to determine the pebble size when doing a pebble count to characterize the stream bed. For more extensive characterizations, stream surveying equipment may be necessary. Bank pins or sediment traps may also be installed in streams for intensive projects. In addition to the equipment previously noted, lake monitoring can utilize some special equipment as well. A Secchi disc can provide a low-cost measurement of water transparency. A Van Dorn sampler allows samples to be collected from a specific depth by lowering via a measured rope and releasing a weight that closes the ends of the container. A fish finder can be used to determine the lake depth. A multi-parameter sonde is also used in lakes with a long, pre-measured cable to measure out to the desired depth of measurement. So now you have a brief overview of some of the equipment that's used in monitoring, and now we want to look at the requirements for watershed plan monitoring. Quality assurance plans are a must for watershed planning. These take time to compile, and they're often over 50 pages. They're project specific, and they're typically prepared by a consultant. You will need to factor in time and labor for someone to develop this document. We'll talk more about quality assurance plans in a later presentation. Standard operating procedures provide an overview of how you're going to go about collecting your data. The Division of Water has SOPs available for numerous different procedures. The website is provided at the bottom of this slide. This table lists the parameters required in the preparation of watershed plans, including the collection frequency and the estimated time required to take the measurement. These parameters, as well as the laboratory parameters, should be discussed with the Division of Water early in the project planning. For parameters requiring lab analysis, EPA-approved methods must be used by the lab. These will be outlined in the Quality Assurance Project Plan, or QAP. These cost estimates were developed based on consulting with the Division of Water, university, and commercial lab feedback. Individual labs' costs may vary, and these are just to give you a generalized estimate. This can help you with your watershed plan proposal development and review. For one site, for 1 year, the average cost is about $2,900. This includes 12 events, additional events for E. coli, and a consideration for field duplicates as well. Having looked at some of the equipment that is used in monitoring, we want to take a brief look at the process for selecting sampling sites and determining the logistics of a monitoring plan. One very practical consideration for watershed planning sampling is timing. Here are some factors to consider when scheduling your sampling runs. For instance, how many sites can feasibly be sampled during an event? This includes considerations such as where's the laboratory, how long does it take to travel to the watershed, and then from the watershed to the laboratory. The hold time, typically E. coli has the shortest hold time, which is 6 hours. And what is the expected time to sample per site? How long does it take your samplers to collect the samples? What's the travel time between sites? During preliminary selection, you're trying to determine your budget, time constraints, focus areas, and other factors. When considering a watershed to monitor, it should be a Huck 12 or smaller. If possible, it's best to choose headwater watersheds because you do not have to consider upstream inputs. In your review, you will want to review available data sources to identify challenges, potential pollution sources, and have some general idea of the types of solutions that would be necessary in the area. We'll work through an example to help get our heads around what's required. As an example for watershed planning purposes, Lower Cartwright Creek in Washington County near Springfield, Kentucky was chosen at random. Lower Cartwright Creek is a Huck 12 watershed, so it is the right size, but it's not a headwater watershed, so we might have to be sure to monitor at the upstream input. This is not optimal, but it is workable. By pulling up the land use in Wiki Watershed, we can see that it includes the city of Springfield in the headwaters, mostly cattle pasture in the yellow color throughout much of the watershed area, and in the brown color we see some row crops that are concentrated near the floodplain of the streams. Searching for the watershed in the Kentucky Health Portal, we see that at least 2 reaches have been assessed by the Division of Water. Cartwright Creek, from 0 to 6.6 miles, is impaired for primary contact recreation, but supports uses for aquatic life and fish consumption. Road Run is impaired, partial support, for aquatic life use. So this tells us that there is a difference between these 2 reaches. Pulling in data from the Kentucky Watershed Viewer, we can see the locations of the permitted dischargers. We've summarized these in the boxes shown on the map. What sort of problems might these dischargers cause? What kind of pollutants do you think would run off of these sites? Where would you place sites in order to capture these different sources? These are the types of things that you need to think through when planning your monitoring. Next, we want to look at the Watershed Watch data portal and check to see if any volunteer monitoring has been done in the area. The portal shows 4 sites in the area, but they're all inactive. These may be good locations to put sites in the future since they have some history, but they don't provide us any additional monitoring data. So having conducted this brief background assessment, you will need to choose potential sampling locations on the map and mark where the potential locations might be. Note that this discussion of where sampling should occur should begin early with the Division of Water. We want to give you a conceptual idea of how to approach the issue. A good way to accomplish this is just to print out a basic map and then add locations as you go through the review process. Take a moment and identify all potential sites, just generally right now, not necessarily thinking of the best ones. Here's a general idea of where sampling could be conducted. The next step is to prioritize these sites. What locations are absolutely essential? What are high, medium, or low priority? Why would you choose these different priority sites? What do you think? Here's the prioritization we came up with. Yours may look a little bit different. The red sites include the mouth of the watershed, the input that's upstream of our drainage areas. So remember, this is not a headwater stream, so you have some flow coming in to it. And we also wanted to capture the city of Springfield. So that's a major land use change that we captured. Orange sites include the tributary to the south of the source water protection area and the permitted dischargers, the mouth of Road Run, which was a divisional water site, and at the Bardstown Road crossing of Cartwright Creek, and downstream of some of the major tributaries along with Cartwright Creek and Bloomfield Road. Green sites include some major tributaries that would be good to catch, and blue sites include some historic watershed watch sites and some tributaries of lesser importance. So based on this exercise, I really want to sample 7 that are either critical or high priority sites. So that would be around, using our assumption, around $20,300 just in lab costs for a year. But how many teams will need to cover the labor costs? So using this watershed, we get an idea of some of the logistical constraints for a field collection. First, we have to identify the travel to the watershed, the time to travel to the lab, and then the minimum time per team. So in this case, it is assumed that it'll take about 30 minutes to pull equipment together and 30 minutes to travel to the watershed. And by searching for environmental labs online, the closest one is about 45 minutes away. And we know that they stop accepting samples for E. coli at 4 p.m. That's pretty standard. So with lunch, that leaves us 5 hours to sample. And assuming our team can sample 1 site per hour, then we could do 5 sites maximum per team. Maybe a more experienced team would be able to move faster. However, flow measurements can take some time. So you can see this gives us some basic logistics for what is possible in order to estimate the time and field costs for a project. If I want to sample 7 sites, I will need at least 2 teams to cover all the sites in the day. Now I can project my labor costs because I'm going to need 2 teams of 2 for 16 events at 8 hours per day based on whatever the labor rate is. And this is an example of how you would go about coming up with a generalized budget for what it would cost to conduct the sampling. A number of selection factors will determine what the final sites are as opposed to those selected in the preliminary analysis. For instance, do you have authorization from the landowners to sample the site? Can the field personnel safely access the site, or is there a gate that gets locked on occasion? In some instances, sites have to be located in remote areas to achieve project objectives. The site should be located in an area where field personnel's safety can be ensured. So special consideration be given to high flow events. Do you have to cross a stream in a storm event, for instance? What about traffic? Can you park in a safe location and access the site? What about debris or steep slopes or ice someone could fall on? Is the site located in a well-mixed zone? Is it far enough below a tributary or a discharge such that if you take one sample, you can represent that reach? Is there another historic site that's nearby that you can benefit from that historic data? What about backwater? If a low flow bridge or a debris jam or some kind of in-stream structure causes backwater, you may want to avoid those site conditions. You want to make sure that your site is flowing throughout the year. So if your site doesn't have flow, it's hard to take a sample. And is construction planned in the areas? Sometimes you can start sampling on a project and then they build a fence or they start a construction project. So make sure you check with the property owners where possible to determine whether future construction is planned. And finally, is there uniform conditions? With regards to streamflow measurements, the site should be located in a uniform reach, such as a riffle or a run, with a constant depth characterizes that uniform flow conditions across the reach. So, taken comprehensively, you want to use these factors to help determine what the final sites are. Let's say we have budget for 7 sites to be sampled by 2 teams. So prior to doing a final field visit to verify, you want to do a Google Earth Street View and aerial review of the locations. For each location, the first thing you need to consider is where to park. Look for a roadway pull-off, a parking lot, or other accessibility. If you cannot park safely, find another site. Here we can see some parking spaces for each of these sites. Then consider how far away you would have to park. If parking is far away, you have to transport equipment to the site. You can see these are in reasonably close locations. If you have to walk upstream or cross over a tributary, remember that some sampling events may be during storms. For critical or high priority sites look great. However, look at this tributary site in the farthest upstream point in the watershed. The only way to access that tributary will be to walk quite a distance over farmland. This makes this site a poor choice. If we decide we have budget for 7, we can move the site to one of our good sites, which has a nice roadway pull-off and trail. So not there, but over there. You can see the access is much better at that site. This picture is just a hand-drawn delineation of the watershed drainage areas to get an idea of what each site is capturing. This will give you an idea of the sort of resolution you will have on the data for BMP placement when the project is completed. If you're developing a monitoring plan and have finalized your sites via collected GPS location, it is now time to work with GIS specialists to develop a sampling map or develop one of your own using publicly accessible tools that we'll cover in a later presentation. One of the easiest way to delineate the drainage areas is to use StreamStats program by USGS. We'll also cover that in a later presentation. But first, remember you'll want to do some sort of erosion survey as well. Take a look at the location of the tributaries and see how much is accessible by road. In this case, you can do a visual survey of erosion of most of the streams pretty quickly. For other areas, you would need to get permission to access the properties. This will take time. You will also be limited by the rate of walking per day and the travel time back and forth to the vehicle to move to a new location. Use these accessibility estimates to determine the amount of time the effort should take in order to develop labor estimates. For example, if you have 3 miles of walking per stream per day times the number of miles that are needed, then you can come up with an estimate of the amount of time the project will take you. At this point, we've been talking about equipment needs, how to select your sites, and some estimates on how much it's going to cost you. But in talking about monitoring planning, one last item we need to touch upon is data quality. There's an idiom that originated with computer scientists regarding data quality, and that is garbage in, garbage out. If you have poor quality inputs, the result will be poor, no matter how good or how fancy your analysis is. Likewise, if your analysis is poor, the result will be poor, no matter how good the data is. So how good does our water quality data have to be for the result not to be garbage? The EPA has defined level of information ratings to evaluate the quality depending on the data type. So without proper quality assurance, data can only be used for screening uses. And Kentucky uses this level of information ratings from 1 is low to 4 is high. For assessment or TMDL, it needs to meet certain thresholds for data quality. And generally, you need to use approved standard operating procedures and a quality assurance plan to collect data that's going to support use assessment or a TMDL, for instance. This chart is taken from Table 3.1 in the Division of Water Consolidated Assessment and Listing Methodology. It indicates the aquatic life use and the human recreational use, that is primary or secondary use, the core indicators, as well as supplemental indicators of those uses. Supplemental indicators cannot be used alone to make a final use assessment. That is, does it support that use, or does it not support, or is it partially supporting? Supplemental indicators can only be used as support. Core indicators are measurements that can indicate that an impairment is present if enough samples and sufficient quality are collected. Human recreational use indicators are pretty straightforward. E. coli is typically used to assess human recreational use. For aquatic life use, macroinvertebrates or fish are primarily used to assess headwater and wadable streams. Two other distinctions should be noted: priority and non-priority pollutants. Priority chemical parameters include a specific list of 126 chemicals that include volatile and semi-volatile organic compounds, PCBs, pesticides, heavy metals, and the like. 65 of these are called toxic pollutants. This is a long list of chemicals found in 401 KAR 1031. Non-priority chemicals include in situ parameters as well as nutrients, alkalinity, chlorine, and the like. As an overview, the Division of Water requirements for a watershed plan must produce chemical, biological, and habitat data generally at a level 3 or higher of the data quality level. This is necessary because this is the level that's needed for use assessment purposes by the Division of Water. The Division of Water is collecting data for watershed plans such that it also can be used for use assessments as well as TMDLs. Some other notable takeaways include the need for a professional biologist for collection of macroinvertebrates or fish. This means that while volunteer screening may be useful for screening for macroinvertebrates, it cannot be used to support a watershed plan. Also, although a quality assurance project plan is not necessary for habitat data, it is necessary for the collection of the chemical data. So what is a professional biologist? These are the minimum requirements that you would need for a contractor if you do not have one on your staff. You may want to use this in a proposal or a request from other folks. We hope that this collecting monitoring data summary has given you some idea of the types of questions that you need to ask when planning to conduct monitoring for a watershed plan. We covered some of the basic monitoring equipment. Do you want to purchase that equipment or contract it out to someone else? We looked at some of the logistics for requirements and some of the costs. This is giving you an idea of what to look for as you begin to screen for your sites. We also talked about how to select sites and look at scaling. So hopefully this will give you an idea of how to develop a budget and the logistics that are necessary for sampling, such as you can come up with a proposal. And we also talked about data quality levels so that you can know how good the data must be in order to be approved for watershed planning use. I hope this has been helpful, and thank you for your time.